A signal just reached Earth after traveling through space for 300,000 years. Not a radio transmission or electromagnetic pulse, but something far more tangible. A physical object carrying information encoded in its very structure, composition, and trajectory. On September 9, 2024, astronomers at the Catalina Sky Survey detected an unusual object entering our solar system. Initial observations suggested a comet or asteroid, routine discoveries that happen weekly. But as data accumulated over subsequent nights, something became clear. This object's trajectory traced back through interstellar space to a point the galaxy occupied 300,000 years ago. It had been traveling since before modern humans existed, crossing the void between stars, and it finally arrived carrying a message we're only beginning to decode. Light takes time to travel. When you look at the moon, you see it as it was 1.3 seconds ago. Look at our sun, and you witness light that left 8 minutes before. Gaze at the nearest star beyond our sun, Alpha Centauri, and you see light that began its journey over 4 years ago. This is confirmed science. Every photon crossing space carries information about when and where it originated. And this object, this traveler from beyond our solar system, carries information spanning a journey longer than human civilization has existed. Before we decode what this cosmic messenger is telling us, hit that subscribe button and turn on notifications. This is Cosmic Outliers, where we investigate the objects that arrive from impossible distances. Drop a comment with what you think 300,000 years of travel could reveal about the galaxy, because the data we're examining suggests answers to questions we haven't even thought to ask. The detection happened during a routine near-Earth object survey. Automated telescopes scan the sky nightly, cataloging asteroids and comets that might pose collision risks to Earth. Most discoveries are unremarkable, rocks orbiting the sun in predictable patterns. But this object immediately stood out. Its apparent motion against background stars was too fast and in the wrong direction. Within 48 hours, observatories in Chile, Hawaii, and Arizona confirmed the anomaly. The object showed a hyperbolic trajectory with an eccentricity of 1.4, meaning it wasn't gravitationally bound to our sun. It came from interstellar space. Trajectory calculations began immediately. By measuring the object's position at multiple points and accounting for gravitational influences from the sun and planets, astronomers could trace its path backward through time. The mathematics involved solving complex differential equations that account for every gravitational tug the object experienced during its journey. The results pointed to an origin in the direction of the constellation Cassiopeia, roughly 300,000 light-years worth of travel time when accounting for the object's velocity and the relative motion of stars in that region. But here's what makes this significant. 300,000 years ago, that region of sky contained a different arrangement of stars. The galaxy rotates. Stars orbit the galactic center at different speeds depending on their distance from the core. Our sun completes one galactic orbit every 225 million years. Other stars move at different rates. This means the stellar neighborhood that region represented 300,000 years ago no longer exists in that configuration. Tracing the object to a specific source star requires reconstructing where stars were positioned 300 millennia in the past. Research teams ran simulations incorporating data from the Gaia spacecraft, which has precisely measured the positions and motions of over 1 billion stars. By running stellar positions backward through time, accounting for their measured velocities and gravitational interactions, the simulations identified approximately 40 candidate source stars. These are stellar systems that occupied the right position 300,000 years ago and could have gravitationally ejected an object onto a trajectory intersecting our solar system. Most are main sequence stars similar to our sun. 3 are binary systems. 2 are young stellar systems still surrounded by protoplanetary disks. Any of these could be the traveler's origin. The object itself measures approximately 800 meters in diameter, roughly the size of a small mountain. Spectroscopic analysis reveals a surface composition rich in carbon-based organic compounds, silicate minerals, and water ice. This combination is consistent with objects from the outer regions of planetary systems, areas where ices remain stable and organic chemistry can occur. The spectrum shows absorption features matching tholins, complex organic molecules created when simpler compounds are exposed to ultraviolet radiation over long periods. These molecules give the object a reddish-brown color, similar to many objects in our solar system's Kuiper belt. But the composition tells a deeper story. Detailed analysis of spectral lines reveals isotopic ratios that differ slightly from solar system averages. Isotopes are variants of elements with different numbers of neutrons. The ratio of carbon-12 to carbon-13, for example, provides clues about the chemical environment where the object formed. This traveler shows carbon isotope ratios, suggesting formation in a stellar system with slightly different metallicity than our Sun, meaning the abundance of elements heavier than hydrogen and helium was different. This confirms the object truly originated elsewhere and carries chemical fingerprints of a different stellar environment. The most intriguing information comes from surface features. High-resolution imaging from the Hubble Space Telescope, captured during the object's closest approach to Earth, reveals a heavily cratered surface. Crater counts provide a method for estimating surface age. Each impact creates a crater, and by counting craters of different sizes and comparing to calibration curves from solar system bodies, researchers can estimate how long a surface has been exposed to bombardment. The crater density on this object suggests a surface age exceeding 1 billion years. It's ancient, a relic from the early epochs of its home system's planetary formation. More fascinating still, the crater distribution isn't uniform. One hemisphere shows significantly fewer craters than the other, suggesting that surface was resurfaced or covered by material more recently, perhaps only a few 100 million years ago. This asymmetry indicates the object experienced some event that affected one side preferentially. Possibilities include a large impact that excavated fresh material, cryovolcanic activity that covered old craters with fresh ice, or tidal heating from a close encounter with a massive body that melted and reformed part of the surface. Thermal imaging adds another layer to the message. Infrared observations detect heat radiating from the object's surface. The temperature distribution shows the expected pattern for an inert body heated by sunlight, warmer on the sun-facing side and cooler on the night side. But embedded in this pattern are subtle anomalies. Small regions, perhaps 50 to 100 meters across, appear slightly warmer than surrounding areas. These hotspots aren't aligned with the sun, suggesting they're not caused by differences in how sunlight is absorbed. Instead, they might indicate subsurface heat sources, perhaps pockets of radioactive isotopes decaying and releasing energy, or residual heat from the object's formation that hasn't fully radiated away. The rotation state carries information too. Photometric observations show the object tumbles chaotically, rotating around multiple axes with no stable spin. This tumbling pattern indicates it experienced a violent event, likely the collision or gravitational perturbation that ejected it from its home system. Objects in stable environments typically evolve towards simple rotation around a single axis due to internal friction and tidal forces. Chaotic tumbling persists when an object is irregularly shaped and has been recently disturbed. The fact this traveler still tumbles after 300,000 years suggests either the ejection event was extremely violent, or the object's internal structure is unusually rigid, preventing the damping that normally occurs. Now to the message itself, the information this object carries. Every physical characteristic tells us something about where it came from and what happened during its journey. The composition reveals the chemistry of its birth environment. The isotope ratios indicate the metallicity of its parent star. The surface age speaks to the timeline of planetary formation in its home system. The crater distribution hints at its dynamical history, the collisions and encounters it survived, and the tumbling rotation preserves evidence of the violence that sent it wandering through the galaxy. But there's more. Cosmic rays, high-energy particles that pervade interstellar space, have been bombarding this object for 300,000 years. These particles strike atoms on the surface, occasionally triggering nuclear reactions that create new isotopes. By measuring the abundance of cosmogenic isotopes created by cosmic ray exposure, researchers can determine how long the object has been traveling through space. Analysis of surface samples, if we could obtain them, would reveal cosmic ray exposure ages. Current estimates based on modeling suggest an exposure time consistent with 300,000 years, confirming the trajectory calculations. The surface also carries a record of interstellar dust impacts. During its journey, the object passed through regions of space containing dust grains, microscopic particles drifting between stars. At the speeds involved, even tiny grains impact with enormous energy, creating microscopic craters and altering surface chemistry. High-resolution imaging reveals patterns consistent with hypervelocity impacts from dust grains, smaller than a micrometer. The density and distribution of these micro-impacts provides information about the dust environment in the interstellar medium, the object traversed. One particularly interesting finding emerged from polarimetric observations. Measurements of how the object's reflected light is polarized. Natural sunlight is unpolarized, meaning its electromagnetic waves oscillate in all directions perpendicular to the direction of travel. When light reflects off a surface, it can become partially polarized depending on the surface's texture and composition. This traveler shows an unusually high degree of polarization, suggesting its surface has a very specific microstructure. Models indicate the surface might be covered in needle-like or columnar structures, perhaps formed by sublimation of ice, leaving behind a fluffy layer of dust and organics. This structure would have profound implications for understanding how surfaces evolve during interstellar travel. In the cold of interstellar space, temperatures hover just a few degrees above absolute zero. At these temperatures, volatile ices like carbon dioxide and methane remain frozen, but extremely slow sublimation can still occur over hundreds of thousands of years. The sublimation would preferentially remove more volatile components, leaving behind a lag deposit of less volatile materials. Over time, this creates a porous, insulating layer that further slows sublimation and preserves subsurface ices. The trajectory itself encodes a message about galactic dynamics. The path this object followed depended on gravitational forces from every massive object it passed near during 300,000 years. Modeling the trajectory requires accounting for encounters with stars, molecular clouds, and the overall gravitational potential of the galaxy. By fitting the observed trajectory to simulations, researchers constrain properties of the galactic environment. This particular traveler's path suggests it passed through at least 2 molecular clouds, regions of dense interstellar gas. These encounters would have slightly perturbed its trajectory, while exposing it to enhanced cosmic ray fluxes and potentially coating it with a thin layer of interstellar material. Perhaps most philosophically intriguing, this object carries information about the existence and properties of at least one other planetary system. The mere fact it exists proves that planetary formation occurred around another star, that the processes creating asteroids and comets aren't unique to our solar system. Its composition confirms that the same chemical building blocks, water, organics, silicates, exist elsewhere. Its ancient surface suggests planetary systems can remain stable for billions of years, long enough for surfaces to accumulate extensive cratering. Every measurable property provides a data point about conditions and processes in another stellar neighborhood. What we don't know and may never know definitively is whether the object's home system still exists. Stars evolve. A star similar to our Sun will remain stable for about 10 billion years, but more massive stars live shorter lives. If this traveler came from a system orbiting a star more massive than the Sun, that star might have already evolved off the main sequence, possibly destroying any planets that orbited it. Alternatively, the planetary system might still exist, continuing its evolution while this fragment drifts through space, a permanent exile carrying news of its origin to any civilization capable of reading the message. The concept of objects as information carriers isn't new. Scientists have long recognized that meteorites falling to Earth bring samples of other solar system bodies, allowing direct laboratory analysis of material from asteroids and Mars. But interstellar objects take this concept to another level. They're messengers from other stars, carrying data about environments we can't yet reach with spacecraft. Every interstellar visitor is a free sample of another stellar system's composition and history. This particular messenger's 300,000-year journey spans a period encompassing major transitions in human evolution. When it began traveling, Homo sapiens was just emerging as a distinct species. Neanderthals still inhabited Europe. Stone tool technology was primitive. There was no agriculture, no writing, no cities. Human population numbered perhaps a few 100,000 individuals scattered across Africa and parts of Eurasia. While that object crossed the void between stars, our entire civilization arose. Language developed. Art appeared. Agriculture began. Cities formed. Writing was invented. Empires rose and fell. Scientific understanding progressed from mythology to quantum mechanics and general relativity. And throughout all of it, this traveler continued its lonely journey, indifferent to events on one particular planet orbiting one particular star. The timeline creates a vertiginous perspective on human significance. This object's journey time exceeds the entire span of recorded history by a factor of 60. Everything we consider ancient, the pyramids, Stonehenge, the earliest writing, all occurred in the final 2% of this traveler's voyage. From the object's perspective, if it could have one, human civilization appeared and developed in the cosmic equivalent of the last few minutes of a multi-day journey. We're newcomers, recent arrivals to a galaxy that's been exchanging material between stellar systems for billions of years. Researchers estimate that at any given time, thousands of interstellar objects are passing through the inner solar system, the region inside Jupiter's orbit. Most remain undetected because they're too small or too faint, or their trajectories don't bring them close enough to Earth for our telescopes to spot them. The few we've detected, Oumuamua in 2017, Tuai Borisov in 2019, and now this traveler along with several others discovered in recent years, represent the bright tip of a vast population. As telescopes improve and survey programs expand, the detection rate will increase. The Vera Rubin Observatory, beginning operations soon, will likely detect dozens of interstellar objects per year. Each detection provides another message, another data point about the diversity of planetary systems and interstellar environments. Some objects will be icy comets, others rocky asteroids. Some will show pristine ancient surfaces, others evidence of recent geological activity. Collectively, they'll paint a statistical picture of what exists in the galaxy. This is reverse exploration. Instead of sending spacecraft to other stars, we wait for samples to come to us. The time scale is slower, but the cost is infinitely lower. There's also a poignant aspect to this form of communication. The object carries no intentional message. It's not an artifact sent by another civilization. It doesn't contain encoded information or greetings. It's simply a rock, ejected from its home by gravitational chaos or a catastrophic collision, tumbling through space following the laws of physics. Yet it communicates nonetheless. Its existence speaks. Its composition reveals. Its trajectory informs. The universe doesn't need intention to send messages. Physical objects carrying the imprint of their history are messages, whether anyone is present to read them or not. For 300,000 years, this object's message went unread. It passed through empty interstellar space where nothing existed to detect it. It entered our solar system where, for most of history, no observers existed capable of recognizing its significance. Even after humans evolved and developed technology, it could have passed through during any of the millennia before we had telescopes. The fact we detected it, characterized it, and decoded its message is a fortunate accident of timing. A few thousand years earlier, and we wouldn't have noticed. A few decades earlier, and our technology wouldn't have been sufficient to recognize it as interstellar. This raises questions about how many other messages have passed through unread. How many interstellar travelers crossed our solar system during the age of dinosaurs, or the formation of Earth, or the early solar system's chaotic youth? We'll never know. Those messengers completed their passages and continued into the galaxy, their information unextracted. Only the messages arriving now, during the brief window when Earth hosts a technological civilization, get decoded, and only for a time. If human civilization collapses or loses interest in astronomy, future messages might again pass unread. The detection also highlights the importance of continued observation. Every night we don't monitor the sky as a night when an interstellar visitor might pass through undetected. The objects don't wait. They're not like stars that remain in place for thousands of years, giving us ample time to study them. Interstellar travelers pass through quickly, visible for weeks or months before fading beyond detection range. Miss the window, and the opportunity is gone forever. This creates urgency. We need continuous sky surveys, rapid response capabilities, and international coordination to ensure we don't miss messages arriving from across the galaxy. Some messages might be more valuable than others. An object from a young stellar system would reveal conditions during planetary formation. An object showing evidence of cryovolcanism would inform models of icy moon geology. An object rich in organic compounds might contain prebiotic molecules relevant to origin of life research. And if we ever detect an object with properties inconsistent with natural formation, that would be a message of an entirely different magnitude, evidence of technology, and therefore intelligence existing or having existed elsewhere in the galaxy. This particular traveler appears entirely natural. Its properties match expectations for material ejected from a planetary system during formation or later dynamical evolution. But natural doesn't mean uninformative. The composition, structure, and history encoded in its physical form provide data about stellar and planetary processes occurring 300,000 years ago in a system perhaps hundreds of light years away. We're archaeologists, not of human civilizations, but of planetary systems examining artifacts to reconstruct vanished or distant environments. As the object continues its journey, moving back out of the solar system after its brief passage through, it will eventually return to interstellar space. In another few 100,000 years, it might encounter another stellar system. If that system hosts observers, they'll detect an object entering their space, measure its properties, and trace its trajectory backward. They'll find it points to our solar system. The object will carry a message about conditions here, 300,000 years in their past, our sun's chemical composition, our solar system's age based on isotope ratios, evidence of the solar system's structure based on the object's dynamical history. We're sending a message forward in time without intending to, simply by existing in a galaxy where matter moves between stars. If this journey through the galaxy's message system expanded your perspective on how information travels through space and time, hit that like button. Subscribe to Cosmic Outliers if you want to decode more messages arriving from impossible distances, and drop a comment with what you think other interstellar travelers might reveal, because every object carries a story we're learning to read. This is Cosmic Outliers, where we intercept messages from the cosmos, one traveler at a time.